Good morning.
Howdy, morning.
Today we're going to go through StudWalls, kind of a specific instance of columns, but of course pretty common in wood construction. And there are a few unique features about them that make it worth, I guess, taking a special look at them. But first, the wood of the day. And I picked hem fir because the example that I'm going to do is based on hem fir. So you can see what hem fir actually looks like. It's kind of a grayish. It's pretty common here in Michigan, although it comes from the West Coast primarily. According to the NDS, hem fir, where do we go here? Well, I had it here a second ago. My page. Oh, there it is. California red fir, grand fir, noble fir, Pacific silver fir, western hemlock. I guess that's where it gets its hem, and white fir. So western hemlock is pretty common. Oh, let me see. Oh, I nearly forgot. I was going to show you some pictures of it. Where'd that go? Okay. I think this works. Somewhere. There we go. Okay, so that's like the piece in your hand. You can see it's a little bit grayish. Pretty clean grain. Few little knot holes usually. It's not as red as Douglas fir, and it's not as white as spruce pine fir. It's kind of in between the two in terms of the actual wood. But it has a definite softwood grain. Is pretty obvious, you know, that very distinct wider grain. This is a image of a western hemlock, I believe, if I got the name, and it goes by Tsuga. Tsuga is, if I pronounce that right, is the Latin for it. We had, you know, the famous allusion to hemlock, where it was Socrates, right, drank the hemlock. That is not this hemlock. In the hemlock, the hemlock that was poisonous that he drank was, I think, a little shrub or something that grows in Greece that had the name hemlock. The tree is totally different species, different plant altogether. So I don't know if I'd drink it. It's probably not that tasty to drink, but I don't think it's the same as what did in Socrates. This, oops, I got the wrong. Get my mouse back over here. Oh, man, so hard to control the mouse on this thing. Can I do? No, can't do it with that. Okay. Oh, there it is. Okay. That one up there in the top is the western hemlock. You can see there are also other bunches of other hemlocks. I think what we see around here is the eastern hemlock. At least that's what I'm familiar with. There's some around on campus. They have, let's see if I got one of the leaves of it, or like that, the real short needle, almost like what you'd have for a Christmas tree or something. Obviously not quite that big. That's the western, but all the hemlocks have these real short needles and real small little pine cones. There you go. There's a better picture of it. Whoops. Okay, so that's probably the end of them. All right, so that gives you a little bit idea of the hemlock, and it is, like I say, it's pretty commonly used structurally. From that one image, I mean, out west they must grow huge, which is probably and pretty straight, which is why they make pretty good lumber. Let me see what this also said. This says there's 6 commercial species, which are probably the same as one I just read. It's cut for lumber primarily in Washington, Oregon, and California, parts of western Montana, Idaho. Okay, so out west. They market as white fir throughout the United States. Really? I've always seen it stamped hem fir. I don't know, this one doesn't really have a stamp on it. But, okay, maybe white fir. It's the wood of the western firs is similar to that of the eastern firs, the true firs, which make it impossible to distinguish the two by examination of the wood alone. Okay, yeah, I guess. So you would think they have pretty similar structural characteristics too. It's primarily used for building, construction, boxes, crates, millwork, sashes, doors. Yeah, I guess the cleanness of the grain is what would make it good for millwork. It's high-grade lumber from the noble fir is mainly used for interior woodwork, molding, siding, sashes, doors, and some of the highest quality is suitable for aircraft construction. Aha, okay, well, if you're into building aircraft, I guess that would be a possible wood. There are other hemlocks. These, they mention here the eastern hemlock, but in the NDS, I don't think we have more than one hemlock. Oh yeah, we do. We have eastern hemlock tamarack. Okay, yeah, so they do distinguish in the NDS between east and west. Eastern hemlock tamarack versus hem fir, and hem fir is the western species. And they also, in the NDS, separate it as hem fir north. There is a separate category for that. Okay, so, all right, so that gives you a little bit of idea of hem fir. And now, see if I can get my, is this thing working now? I've played around with the, it was working a second ago, and somehow I deactivated it using the other mouse, right? How'd I do that? Huh. Okay. I don't know. Okay. Sorry. Little detour here. I've got to turn my pen back on. It's not on. Whoops. Okay. Calibrate. Okay. Monitor. There we go. One of the little hassles of this thing. Sometimes it's and now I got my little arrow back. Okay. Hooray. All right. Let's see here then. And now I lost my mouse. There we go. You have one or the other, I guess. Didn't like to do both. Okay, so I'll show you a couple other books that I was looking at the other day. I just got a copy of this myself. This is published by the American Wood Council, same people as produce the NDS, of course. This is their wood frame construction manual. Wood frame. They make several different little manuals. There's one specifically on wind and seismic that has some really weird name, WizBid or something. I can't quite remember. It has like 6 initials across it. This is primarily, wood frame construction for light residential construction. So it gives a lot of some specifications on StudWalls. It has a lot of tables that you can use with StudWalls. The tables, of course, are pretty specific to, they give you the loading, so then you have to match that loading, which gives you a lot of tables. They give a lot of details in the construction, both of stud walls and also rafter construction, that kind of. It's all based on light framing. So I'll look. I think I've got a copy of this up on Canvas, but I'll check and see if I can't get one up there for you, because that's pretty useful. The other thing, as long as I'm on these additional things, they also make, the American Wood Council puts out manuals. And it used to be, there was just one manual. And now they've got, I think, several. This is the 2018. I don't have a bound copy of it, but the 2018 Manual for Engineered Wood Construction. Okay, so this is a lot of the glulam, composite, all the manufactured, what they call engineered stuff. This is the manual for, this is also engineered. Take it back. Although in this version, this is the 05, they have, I think I mentioned this in that, the last lecture we did on columns, we didn't meet, right? What was it? It was all snow. That was it. I didn't get here because of the snow. And in that video, I was looking over it. In the end of it, I mentioned a table. This is the table that was in the 05 edition. But then in the newer editions, I guess this is the 18. This is the same thing in the 2018. They took this table out, which I was kind of surprised, because of all the tables, I thought this one was pretty useful. You could just go down for the size of the column and the grade of the wood, and the height. So you've got the cross section. This is 8 by 8, 8 by 10, and the different grades, and the height up to 16 feet, and the different wood types. And then you could just pick this capacity. So very rapidly you could get a sense of the strength. Or you can, what these tables are really most useful for, I think, is the other way around, for design. If you have a capacity that you're shooting for, you find your numbers in here, and then see what matches your numbers. That's much faster in terms of design than kind of trial and error, or I don't know how else you'd really easily do that in design. You just have to pick something and try it. And ultimately, I have a limited kind of trust on tables anyway, because sometimes I'm not totally sure how they got the numbers and why they decided to leave it out after 2005. Is there something wrong with the table? I don't know. So I think I'd always check the numbers afterwards. I don't think I'd rely entirely on the table, but they're good for a quick reference. If it's a initial design and you're going to do it over again anyway, fine, in the final version, this gives you an initial size. So that's kind of nice. Okay, so those are the manuals. As long as I'm on these things, I think I posted this. There's also, the American Wood Council also makes a little booklet here, and this is the 2018 edition, 2015-18, of examples. So in terms of making sure that you're doing the calculation correctly, this is kind of helpful, because you can find, they go through just complete examples of sizing members, or, there'll be columns, beams, whatever, choosing nails, choosing fasteners. So, it's not exhaustive, of course, but it does at least give you some guidance that's pretty reliable. I mean, yeah, you would think it's reliable. It's coming from the people that wrote the code, right? So you think, okay, they're the source. I've mentioned this way back at the beginning of the course, and I'll mention Breyer again now, because we'll do an example that's out of this today. This is probably not the, when was this? This is the 6th edition. It's the newest one I have. This is 2007. Oh, 2007. Okay, yeah, he's probably got a newer one out. But this book's been around forever. When I was a student, sitting where you are, we used Breyer. It was probably like the 2nd edition or something, or the 1st edition. But he is pretty much the reference on wood as far as textbooks go, at least in the U.S. certainly. So that's interesting. And I'll show you. We'll do an example that came from him, and I didn't agree. I was kind of surprised at some of the things he did, actually. So we can talk about that. Okay, so looking at StudWall systems, basically it breaks into 3 types. There's also, in terms of the exterior, in terms of exterior walls, they very often also act as shear walls, right? This is they receive the wind load directly in bending, potentially, right? So they'd be combined stress, compression, and bending. And then they also, what's probably the heavier load, or more to design with, they take the shear in the opposite direction. So if the wind is blowing this way, then you've got the shear resistance, the lateral resistance, as the wall's going parallel to the wind direction, right? So those you have to design as shear walls, and we'll do that a little bit later. That's a whole separate kind of topic, getting into those exterior walls and combined stress and everything. So I'm not going to do that right now, but that's what's in the exterior walls. The interior load-bearing walls is what we can look at. This is kind of a nice little image they point out that, yeah, it's a good idea to put them over something that's going to hold them up, right? I mean, you would think that would be sort of a no-brainer, but you do have to pay attention. If the load's coming down on these, they actually are load-bearing. It has to transmit through the floor to something below it. If it's non-load-bearing, this is the non-load-bearing version, then it's not really so critical. Then it's just a partition wall that doesn't have any more weight on it than the dead weight of itself. So then those are not so critical. There are specifications, that's what these are here, that call out some things, and this is worth taking a quick look at. This is out of this document, the WFCM. And there were a couple things I thought that were, this table they mention a whole lot, and it's a design table that's in there for StudWalls. I don't know that it's not, I looked at it, I thought, well, I don't know, it's not that useful. But, okay, at any rate, that's a table where you can select StudWalls. What was probably interesting in this is some of their criteria, notching and boring, that you would want to pay attention to. If you have a stud, right? Whoops! Look, it notched itself. How'd that happen? What an intelligent pen. Okay, and you're going to cut a hole in it like that. There are limits. First off, you should not cut the hole there. Right? That would be a no-no. You should not cut the holes the holes should be cut in the middle third. I think that's, or no, am I getting this backwards? Sorry. Exactly backwards. They should not, that would have been okay. They should not be cut here. That's where the bending would be the most, right? Or even in buckling. If it's buckling, that's where the critical strength would have to be. So you don't want any holes in the middle third. So in the outer thirds, they are, so where does it say that? Shall not be located in the middle third. Okay. In the outer thirds, you can have them, but there are limits. Let's see. Shall not exceed 25%. This is notches. So you've got two things. You've got notches, right, which would be a chunk out like that, out from the edge, and you've got hole. This is a notch. And you've got holes, oops, which are like that. And the holes can't be larger than 40% unless, I think there's an exception. Yeah, here we go. If they're doubled, then you can go to 60%. So 40% on, if you've got a 2x4. Hey, where'd all my 2x4s go? I forgot to bring them up here. All right, well, that's okay. If you had if this were a 2x4, and there were you're cutting a hole through it, then 40% I think is less than 1.5 inches. It's not that big, right? And should not be closer than 5/8 to the edge. So they're not. You've got to have a distance here. I think I've got a slide actually that shows all this. This is it. So here are the notches, right, that you can't have, and these are the edge distance of 5/8. Okay, you got that. And if it is a double stud, then you can go to 60%. I guess these are the 2/5 diameter. That's kind of confusing. It made more sense just to say 40% and 60%, right? This one's 60% and this is 40%. Okay, so those are the notches. Let me see. Otherwise, studs need to be continuous. Okay, you would think that would be pretty self-explanatory too, or self-evident. If it's a compression member, you can't just butt end two together. That's not going to work. Finger jointed is different. Finger jointed is done, but they have then the capacity of a continuous member, supposedly, right? This is where, didn't we look at a little video of those where they make those, or yeah. Okay, so that's a little bit different. This is just talking about butted together. Let's see, top plates. Top plates are usually doubled. There are, double top plates. But they say in this table 29C, they also have instances of single top plates. I think what you have to do, if you have a single top plate, there are a couple problems. If it's an interior wall, it may not be so critical. The things that make it difficult is if you've got joists coming. If it is load-bearing, yeah, it must have joists on top of it then. So if the joists are not landing, if I've got it supported like, the stud's coming up here and the joist lands in between them, obviously that little single 2x4 is acting as a short beam. And if you've got you could have a 24-inch on center spacing as a maximum, I guess. That might be a little dicey. So usually they're doubled for that reason. The other reason they're doubled, and this would be on exterior walls, when they act as a shear wall, the top and bottom chords have to take tension and compression, right? In that we'll look at that later, but that's how that's going to work. And on the bottom one, it's attached to the floor, so that kind of joins it. If they're, when you have a break, the two kind of are joined down to the floor. But up above, that's not true. There's not, you just have a plaster ceiling or a drywall, so there isn't anything that's really joining them. So you have to when there's a splice, you have to have a lap on top of it to join that, right? And if you don't do that, then people like Simpson Strong Tie or whatever their name is, they make special metal connectors that you'd have to use to join. If you just have a single top layer, somehow you have to join that then, right, to get the continuity. This is on an exterior wall primarily. Okay, so those are the top plates. So that's why top plates are almost always doubled, ones I am familiar with. Bottom plate is usually singled, a single layer. And that, the specification they put on that is it's got to at least be a 2x member. You can't have a little board down there. That's not the idea. The other thing, when those come down, well, at both ends, actually, it's the same. There's a bearing stress, right? And I think we talked about that. That bearing stress it's almost like a deflection limit. They base it on how much crush they want to allow, because as that crushes into the plates, the wall sags, right? So how much you want to tolerate, and I think it's, wasn't it 3/8 doubled or something, or 3/8, I forget whether it's 3/8 or 6/8, is, you know, because it's top or bottom, or whether it's just the bottom or bottom and top, adds up. At any rate, that amount of crush is what's considered as a serviceable limit. You can, they do make, if that's a problem, if you've got a capacity problem and the bearings controlling it, rather than, I mean, what could you do? You get stronger wood, I guess, or you could get, space them closer together. Those might both be expensive solutions. They make little metal plates that you can shim in there that then provide a wider bearing surface. So that is an option too. That's specifically made by a product by probably Simpson. Again, they make everything for wood, and that's a solution. But it's pretty rare that usually is not such a problem. Okay, so there are those guys. Okay, this is, I wanted to give you, since I don't really have, in fact, I even forgot to bring up my little pieces of wood here, to show you. I thought I'd at least look at this video. It's not the world's best video, but this guy at least explains the pieces of a wall. So it's maybe worth a look. We can watch it if I can get it to work. Let's see.
So we're going to start down here at the bottom. The very, very lowest piece of a wall is called a bottom plate, or a mud sill. The purpose of this plate is to anchor the wall down. As you can see, we have small bolts like this that are embedded into the concrete. They look something like that right up there. We drill a hole through our mud sill when we're plating for where that anchor bolt goes, and then we tighten down that anchor bolt and it fastens this wall to the concrete. Now, since this plate is touching concrete, you can see that it's directly on concrete. It has to be a treated piece of lumber. Now, the bottom plate here is also fastened to the studs here. When we frame our walls, we have the bottom plate laid out, and we have the top plate laid out. We pin through the bottom plate into the studs with 3 1/4 nails, 16ths. And that's what holds these studs down to the bottom plate. We're going to jump up to top plates real quick and discuss those. We have 2 top plates. It's double plate. We have 1 plate, and we got 2 plates. The purpose of these plates is to tie walls together, and a few other reasons that we'll get into in a second. So the first top plate, the very first top plate up there, that plate is going to be used the same way as the bottom plate. You're going to nail through the first top plate into the studs. After the wall is complete, you're going to go ahead and put that second plate up there. That second plate is done for a few reasons. As mentioned, it's to tie those walls together. And the second reason is for load-bearing purposes. So when we pull our layout, some of the trusses will land on top of studs. That's perfectly fine, that's great. But others, like this one here, doesn't. The reason you have those double plates up there is to prevent the top plate from sagging. If you only had a single plate, although it's only a 16-inch span, that truss and the weight of that roof could push down through that fairly easy. So you have that double plate, that beefed up plate all the way through, for load-bearing purposes to carry the roof. Now, there are advanced framing techniques where you stack everything, but that's not seen too often here in California. And since the top plate isn't touching concrete like the bottom plate, It doesn't need to be borate treated. It can be regular old Doug fir like we use for framing. The only plate that has to be treated is anything that goes up against concrete. And when it comes to framing, when you do your material takeoff, you're going to want to order longer plates. Your goal is to get the least amount of breaks as possible. You don't want 20 breaks throughout a 50-foot wall. So we'll order 16-foot or 20-foot plate for bottom and top. So now that we've discussed our top plates and our bottom plates, let's run through everything in between. So whether you're in construction or not, 99% of people understand the term stud. This is a stud right here. It runs top to bottom, full length, no breaks in it at all. Now the purpose of a stud is to construct a wall. 16 or 24 inches on center is standard, pulling from the edge, laying out all your studs. Now these studs are all laid out 16 inches on center, meaning if you hook this stud right here to the next one, it works out to 16 inches. The reason you do that is because 4 studs works out to 48 inches. So on the exterior here, our plywood, or our OSB, lands and breaks on studs. That's a totally different topic though. The studs are used to carry the weight from above and push it all the way down to the bottom plate. They come in many different sizes, 2x4, 2x6, 2x8. Now studs come pre-cut from the lumberyard. Depending on the size of the wall, you've got 8-foot wall, you're going to have 92 1/4 as your pre-cut stud. 9-foot wall, you're going to have 104 1/4. 10-foot wall, 116 1/4, and so on and so forth. Depending on how big you get, you might have to custom cut them. We custom cut everything for the great room in this build.
Okay, the reason they come in different heights is they're adding when you add on the sill plate at the bottom and the double plate at the top, that's 4.5 inches, right? That decrease, normally that would be the ceiling height. If you look at those rafters there, let me see, do I have my pen back? Okay. Well, yeah, so that's why when you go to the lumberyard to buy them, they're pre-cut to make an 8-foot ceiling height. But that's then you have to subtract off the sill and the plate. Okay, that's one thing. The other thing he didn't mention, but you see in here, are all the blocking. Of course, if this is it's only 1.5 inches thick, and there is that L/D limit, right? So to meet that L/D slenderness limit of 50, you've got to have blocking in there somewhere. And you can get away, if the sheathing braces it fully, then you can leave the blocking out. But in my mind, that means sheathing on both sides. I don't know, but although I've commonly seen just what, well, here he's got the blocking. Okay, so he's good. But where you'll put the sheathing on the exterior and then leave the blocking off. But I don't see that's fully braced in my mind. That's like, okay, in a floor that works because there's only one compression edge, right? You put the flooring on and you've totally braced it. That's no problem because the bottom's in tension. But here, that's not the situation. You've got both edges in compression. So you're bracing one, but you're not bracing the other. So, okay, it's half braced. I guess, maybe it works, but I would be a little bit nervous about that. If it's really in compression, what's keeping this bottom from warping out of position? It doesn't seem, I would not count that as fully braced. I'd want to see, if I'm saying it's fully braced by the sheathing, then there should be sheathing on both compression edges. Anyway, or put the blocking in. For heaven's sakes, is it that difficult? You can see they staggered the blocking there. That's pretty commonly done because it's much easier to install, right? He can then you can just nail straight into it or with a gun, rather than if they lined up, then you've got a toenail in, right? You got to come in with nails on the diagonal. So it's just a little bit easier if they're staggered, I would guess. Maybe that makes it on the interior when you go to lay the drywall on, if you're trying to hit them. But I don't think you hit those necessarily with the drywall. You just hit the verticals. So, with nails or screws. Okay, what else can we notice here? He's got these. Oh, you might look at this too. Look how this is framed. Against the window, you've got a double piece here. This piece normally you've just got one that goes continuous all the way up, and then the next one frames into the window. But here they've got two. Okay, maybe that's even better. And then this one is under the window. This frames into the window. So you see there's quite a bit of wood around that window, but I think it's required to be doubled. They've got names like a jack. Maybe the one underneath is a jack, and the one that's continuous I think is called a king stud and a jack stud or something like that. This must be the jack stud. And this is the king. I guess here they've got them just a single one. So the king goes all the way through, and the jack is under the window, but they are doubled. And then this is above. This is also, I guess, a jack or part of the window frame. Okay. All right. So, what other? Oh, he was talking so much about the concrete floor. Yeah, if it's on a concrete floor, that's all true. Of course, very often it's not. It's on a wood floor. It's up on, I think more often it's up on the joists, right? It's up on a wood floor, so then that's not such an issue. Then you don't have the problem. What we'll talk about in the example is whether this plate and the top plate potentially rotate with the buckling member or don't, and I'll show you that in a second. The other thing he just mentioned in passing was this advanced framing. This is something that's come out with APA fairly recently. They're promoting advanced framing, and let me see if nuisance to get these things to go. Oh, it's going. Okay, however that happened. All right. Amazingly, it's working. Okay, so this is except I don't have my hand. Now watch it go off. It did. All right, I'm not going to try and mess with it again. But if you go to APA's website, you can see this lovely little video that all it does is flip between the two types. The conventional type is primarily based on 2x4s, maybe 2x6s. This one, the advanced, requires 2x4s. So 2x6s. If you have the 2x6s, somehow they are letting you get away with a single top plate. Okay, the 2x6 is wider, whether it really is able to carry a truss coming down at, they're saying 24 inches on center. Okay, I guess so, but I would be a little bit, I would want to double check that. If the weight, the reaction of that truss coming at the center of a 24-inch span is really not going to be a problem. Okay, but they do have two studs at the corner. That's with the 6s, 3 studs at the corner is usually, a double one, and then one this way. So you got 1, 2, 3, like that. And part of that, it stiffens it, but it's also to give you nailing surface to be able to get the stuff attached. And this one has multiple jack studs. These are the jack studs here. Oh, I guess these are all jack studs. Okay. These are the jacks. Okay. So it's got multiple ones. In that brown version, it only had one, I think, in the center, maybe. I'm sorry. These are the cripple studs. This is the jacks. Well, I don't know. They've kind of illustrated this a little bit weird. I would have called these the king studs, and the jack studs would only have gone up to that level. Okay, whatever. And the cripple studs, these are the cripple studs down here. How do we spell cripple? Cripple studs. And this one that I'm pointing, this should be the jack stud, the one that's at the edge. Anyway. For what it's worth, if you come across that term, advanced framing, that's what they're talking about. They're just trying to limit, and I would think that's mainly limiting, all right, I guess it's limiting material, limiting labor a little bit because there are fewer You're putting them 24 inches on center. But then obviously the 2x6 is going to cost more than the 2x4. So, okay, I don't know if it's that much of it. It's probably why it's been rather slow. Like he said in California, whenever that video, that was a pretty recent video, they don't use it. So, okay, it's not, it doesn't seem to be catching on that much, but that's what that's about. Okay, so now let's see if we can get through an example. Couple examples. I want to do one capacity analysis. We'll do one as an analysis example, and then we'll do one as a design. Okay, so in this would be a situation where you've got everything given. I mean, the design is completely worked out. The spacing's given. All the conditions of use are known. The only thing you're looking for is how strong is it. We're just going to determine how strong it is. So you can look up all these values in the NDS. In the table, you need not too many. FC, you need E min for CP. Calculate the slenderness ratio, has to be under 50. Otherwise, then you've got to put your bracing in here so that it does meet that 50. Find all the adjustment factors except for CP. Then you calculate CP. You have to get all these first, right? Because these all go into F asterisk C. So you have to have all those and then get CP. Then you, once you have CP and all the other factors, you can get the F prime C. And you set that, if you're doing the looking for the strength, then you set the load. You're looking for the load. I'm sorry, equal to the maximum strength. So this would be the maximum strength, right? The strength. And you set, maybe my pen's dying. And then you set the load. This is coming from the load. So you set that one equal to the max. You max out the strength, max out the load. You're maxing out the load to get the capacity, the load capacity. Then that's the stress. You multiply it by the area of one stud, right? And that'll give you the strength per stud. And then you can find the PLF. This would have a PLF load on it, right? On that top, based on the stud load, what the stud can carry. And you just find what that is. You convert this per stud to a PLF load. The last thing would be to check the bearing. Make sure that's okay. Okay, so this is an example actually that I swiped out of Breyer, and I made one. In going through it, he did one thing differently than I would do, and I was kind of surprised by it. But I went ahead and did it the way I'd do it, and just partially just to see what the difference would be, how much difference it makes. What we've got here is a stud. He does simplify it by putting sheathing on both sides, so we know it's not going to have the weak axis is totally braced. So normally, very often, the weak axis would control, right? It would buckle in even as an S inside the wall. But if you totally brace it, and he's got, okay, I'd agree with this, he's got sheathing on both sides, okay, then you're going to have strong axis buckling. So then we're certainly going to have the buckling we'll have to look at LX, right? It'll be over the stronger depth, the 3.5 inches. Wow, man, this pen is getting weird. Okay, Right, and he gives us he says there's no problem with moisture, no problem with temperature, no incising, and we're looking at a snow load. So CD is going to be 1.15. Okay, and it is hem fir. Okay, so we're going to base this on hem fir. Okay, the total height is 9.5 feet up to the top. And where he and I differ is in that height. I would assume that maybe I'll go back, if it's buckling in this way, I'd take the maximum length and assume that the top and bottom plate rotate with that you've attached. If you've attached the plates firmly enough to the top and the bottom of that stud, if that stud is rotating in the strong axis, I think it would pull the plate. And in my mind, I think it probably would, or potentially could, at any rate. Maybe less on the bottom if it really were securely fastened to the but you usually don't you don't put that, it's not that securely fastened. There's just a bunch of studs underneath, joists underneath it. So maybe you're putting a nail in each joist for that bottom plate, and you probably fasten it more securely to the stud. If you built it on they build these things like that guy was saying, very often you'll tilt it sideways, and then you have the bottom plate here, and you nail into it like this with a couple of nails, not just one, but usually at least two, and then tilt it up. I mean, that's just, I think, pretty much standard practice. Well, that's a pretty firm attachment. So in my mind, I would take the maximum height, plus it's conservative, right? And oh my goodness, I would, for all the times that I've been in a situation where you accidentally, or there's some other thing that you don't foresee that comes into it, it's better to, not be right at the limit, right, in terms of strength. So I would tend to take the full height. I did take the full height as this effective length. Breyer, interestingly enough, didn't. He took the actual height of the stud. He took that height. So now I would agree on the weak axis. I would definitely take the actual height, because there it's you've got the plate here. It's bending this way. Okay, yeah, I see. It's probably not going to do this so much as it's just going to pull those nails. Okay, I'd agree with that, but I don't know in the other way. So it's up to you. We'll see what in the end what difference it makes. I was trying to find some confirmation in here. I'll keep looking. I'd be very interested to know what what either APA or the American Wood Association, if I could find an example where they clarify that. I'll let you know. Then maybe I'll change my story if they agree with Breyer, but I don't know. Okay, so we look these things. Step one, we said we look these properties. This is for hem fir, right? So I think it was it seemed like it was a stud grade. It was some weird grade. What did he say it was? Standard grade. Standard grade, if you look in here in the supplement, standard grade is a stud. They had these categories. Well, it's below stud. It's not stud grade. There are categories below here: construction, standard, and utility. So standard grade is one of those grades down there. Okay, so it is a grade in the NDS, and we do have these pull out of that table. Okay, that's good. Like I said, I took the full height, so I'm using the full height then for my LEX over D gives me a slenderness of 32. Okay, so that's way, well, I don't know, it's not that small. It's more than half of the 50. So if you think of that, right, I always kind of think of this thing is looking like that, right? So with the middle somewhere in here. So I'm on the lower side of that curve, right? This is the CP curve. So I'm on the this is the L over D, and this is CP. So I'm on the lower side. This would be, out here would be 50, right? And this would be totally braced. So 32 is edging a little closer to 50. Anyway, we'll see where that comes out. So you would think, I mean, just as a guess, it's going to be maybe less than 0.5, right? This is 1.0. This is 0.5 in the middle. So, okay, maybe it's always nice to kind of guess numbers before you calculate them, so you're not, if you're totally surprised, you can wonder. Okay, so as far as adjustment factors, we've got the snow load that we're going to put on it. All the others are 1. You need to look this one up. This is in the supplement. I didn't actually show it, but there's that table, this table here, and I can read it for you. You have to make sure you get the right grade. Construction and standard are both 1.0 for compression. So that's where that's coming from. That's table, well, that's the size. All right, it's in the supplement. All right, okay. And this is incising. Okay, no incising. Okay, so for E min, we do have to try to remember to at least think about the factors. This is 1, 1, 1. So in this case, E prime min is going to be the same as the tabulated value. All right, so we got those. Next, we want to take a look at CP, this lovely equation for CP. We got to get the Euler stress. So this is the actual Euler equation, right? That gives us that as the buckling stress. Then we calculate the FC asterisk. So this is from the straight FC value, and then CD, and then all the others are 1. So that comes out as that. The ratio is 0.2. You can calculate, I mean, just in terms of doing this calculation, if you notice, that is the same as that, right? So you can calculate that once and then square it, right, is what I did. And then square it there and then calculate that at the end. This value of C is based on the type of wood, right? Whether it was glulam, or I think there are a couple other options, but that's just given. That's given in here, right? As this is all in. Yeah, it's in section 3.6. Oh, sorry, 3.7. 3.7 of the NDS. So they give you that value of C. Okay, so we run it all through, and yeah, it was pretty low, 0.2. So I was thinking it was kind of in the middle. I was going to say less than 0.5. Yeah, it was certainly less than 0.5. All right, in a way, I'm not too surprised. I think it probably is about that. Okay, then we have that value, right? So there's our CP. Now we can get the, and the others were all 1. I didn't write out the ones that were 1. This is the CD, of course, and that gives us our F prime C. So then this is the area of one stud, right? This is our F prime C, and that gives us the P. So that's the force on one stud, 1695. Okay, so then you've got the studs spaced at 12 inches, 16 inches on center. So it's just a ratio. The stud per the spacing 12/16 will give you the PLF. So I'm spreading it out, right? If they were 12 inches on center, then the PLF would be equal to the stud strength, right? Because you'd have a stud every foot. If I spread them out, it's got to go down a little bit, because if I had them 24 inches on center, it'd be half, right? And 16 is somewhere in between. So that looks good. So that's my PLF load that I got. Just out of curiosity, or just as a point of interest, I said that Breyer, and he did the same example, but he used the full height, right? No, he used the, I'm sorry, I used the full height. He used the stud height, the actual stud height. So he left off the plates top and bottom. And the difference it made is he got, if I can, I don't know if I should write it down here, but Breyer's number at full height. Okay. No. Stud height. Still get it confused. Stud height. Right? He got 1371. So 100, there's 100 pounds, 100 PLF difference. And that comes out to about 7 or 8%. It's not negligible, I don't think. I mean, 7%, come on, that's a bit. So, you got to kind of think, how conservative do you want to be? I don't know. That's why I say I'd like to track down an example from APA and see where they stand on that. I mean, I tend to be a little more conservative with it, but Breyer, he's going with the 7% higher number. At any rate, that's where that falls out. And I can imagine in practice you'll find people going either way. I don't know that I've never seen it written in the NDS which one you're supposed to use. I'd love to. If any of you ever find that in the code itself, let me know, because I don't think they specify it. But APA tends to do a lot of testing. I can imagine somewhere along the line they've tested full stud walls, and they have a sense of how that actually. I mean, that's how you really have to know, is physically test it and see how it goes. Okay. Anyway, well, for what it's worth. Finally, then we have the stud bearing, and here Breyer was he also kind of disagreed with me on this. I couldn't believe it. After being so unconservative about the stud height, he refused to use CB. Okay, if you've got the stud coming down, it's got to be at least, 6 inches away from the ends. This is, like with this is why with a joist, we don't use CB, because it's right at the end. And you're not crushing both sides, you're only crushing one side. And so I think for that reason, they say, okay, then don't use CB. Take the full, don't reduce it. Because you're reducing the area. But if you've got the studs, normally a stud on a plate, you've got the plate and the studs are coming down here. They're not at the ends. Well, Breyer says, well, they might be at the ends. So for the one stud that's at the end, he refuses to use CB. Okay, so yeah, that's true. The stud on the end should not use CB, but all the other studs are not at the end. So I don't know. Again, so I went ahead and used CB. Maybe I'll rethink that. Maybe Breyer's right. I'll be the possibility that the stud might be at the end. Okay, so you can see whether you use that or not. I could say this: not at ends. That's ends of the sill plate, right? Okay, but then of course then the illustration, this came out of his book, then the illustration he uses is not at the end, it's actually in the middle, so he should have used CB for that. Okay, so you put these, this was out of the table, right? I mean out of the NDS. You put the factors on it, these are all 1. This one I use 1.25, which is for a 1.5 inch member, that's that. And then you put that, you get the strength of the stud. You could just compare, oh, I guess I did. You can compare that strength of that stud. I guess you could just compare the stress. Look at this stress versus the stress CP and make sure that this is bigger. But you can do, I just calculated strength per stud. So this is the capacity, right, is what I'm calculating, the strength capacity. So the bearing capacity can be up to 2,600, and I'm only putting 1,600 on it, so that would be okay. There's not a problem with bearing. Okay, good. Man, I talk too much, don't I? Think we can get through this in 10 minutes? Maybe. This is StudWall design. It's very similar. The main difference is at the end, we don't know the spacing. So we have to find stud, I wrote this wrong. Find the allowable spacing. We want to find the stud spacing is what we're looking for. And that's really, all these other steps are pretty much the same. It's just when we get to the bottom, we change, which somehow I didn't get that changed right. Okay, a little bit different example. This one is maybe a little bit more typical. Here again, the stud height is 10 feet, but if you count the top and bottom plates, it's up to 124.5 inches. So I use this for LX and this for LY, right? You can look these values up in the NDS table. This is for spruce pine fir. It's dry, right? So CM, man, equals 1. Dead load, live load, so CD equals 1. We'll take the bracing as like this, so KE equals 1. Whoops. Okay, and it is a stud grade, I think. Where, oh, here it is. This is the grade. That's not just a stud, it's the grade. Right, in the commentary there is a stud grade. Okay, so that's what I'm using. And for CF that comes out to 1.1 in compression. Okay, so the only one I'm not sure of then, I don't know, is CP. So you got to calculate CP. Oh, here, this just verifies these. Here's the stud grade. It's a 6, right? It's a 2x6. Okay, so that is this guy. Okay, so there's the CF. That's CF. Okay, here is. Okay, we got those out of the table. This is looking at the slenderness ratio. For using the full height, I get 22, so it wouldn't have made any difference even if I had not used the full height. The other one is controlling in this case. So has a slenderness of 26.7. Okay, 26.7, again, you kind of think, where does that come? All right, if this is 50, 26.7 is right about in the middle again. So it's going to be probably less than 0.5, or at least around that. So we go ahead and calculate CP. This is that Euler stress. This is the FC asterisk and the ratio of the two. And then I didn't write out the equation here, but that's a big equation. And it came out, in this case, slightly above 0.5, but it's down there in the middle. That's slightly above 0.25. So, okay, that looks good. CP is 0.55, so we put that on there. It brings our F prime C down there. We calculate the, this is the per stud, right? This is using the stud area of, this is a 2x6. And we come out to that. Okay, 3,000 pounds per stud. And then if we want, we were going to then look at the spacing, what the spacing was, right? So you're saying the required is that 2,500. That's in PLF, that's per foot, so that's one, that's in at a foot spacing. But I'm able to carry per stud that, so my spacing, if my stud carries that much, would be S. And you just do the ratio. That comes out to 16.06 and you round down. So it came out very close, kind of perfect example. So I'd use 16 inches on center. That would, and that's it, that's the design. If that's, and normally, I mean, that's, you might design the wood. I mean, that would be the other thing, obviously. You could pick a grade. You could pick, usually the decision of 2x6 or 2x4 has more to do with the construction, whether you're running plumbing through it, all those notches and holes, you know, how much of that's going on. Maybe also the strength. Obviously, it's stronger. This is just the bearing check. Again, I should be able to pull that off. It's 1.25, right? So I've got my 1.25, and it comes out to, there is no CD, right, on bearing. That's an instantaneous crushing, so you leave CD off of that. Okay, so, and then based on 16 inches on center, right, that's my actual stud load. So figuring the load due to the stud, it's only 40, this is capacity, then you could kind of see it as that. And I've got a capacity, it's not going to crush until I get to 531, and I'm only at 404, so it's okay. So that would be safe. Okay, so that gives us a little bit of a run through with stud walls, right? What do you think? Are you going to do them with the full height, or are you going to do it just the height of the stud? I don't know. I have to think about it some more. I hate to disagree with Breyer. I've never disagreed with Breyer. I hadn't noticed that he'd done that. I have to go back and look. But I'm pretty certain I've always done it with the full height. So somewhere along the line, somebody must have convinced me that was a better way to do it. I mean, it's obviously more conservative. It's not that big a deal. But it is not negligible. 7% was the difference. So, okay. That'll be it for today. I have to have a look at what he's looked at the homework. What's the homework this week? Something. Columns. It's just columns, right? But I don't think it's a stud wall. Maybe we'll have to look. I'll look. All right. Have a good week.